One. So after here in the last class we discussed about the correlation, what is autocorrelation, what is cross correlation. Okay, what is the relation between correlation and convolution. After that we will see the energy spectral density, and now we are going to see the interpretation of energy density. So as we already know that energy of the signal x of t is given by t equal to 1 by 2 pi integral minus infinity to infinity uh, mod x of omega square d omega. This is equation number 1. Here x of t is the input signal, r of t is the response, and h of t is the system function. So the Fourier transform of x of t is x of omega, Fourier transform of r of t is r of omega, and Fourier transform of h of t is h of omega. Then Fourier transform of response r of omega equal to uh, Fourier transform of x of t into Fourier transform of h of t. That is x of omega into h of omega, or h of omega equal to r of omega by x of omega. Okay, or r of omega equal to x of omega into h of omega, where E naught is energy of the output signal, r of t. So it is equal to 1 by 2 point integral minus infinity to infinity mod of x of omega into h of omega whole square d omega, right? So this is the energy of the signal r of t. Since h of omega is 0 everywhere except over a narrow band delta omega where it is unity, which is as shown below. It is like this. So this is h of omega having the uh, band delta of omega like this. So f of t is the given function varying from minus t by 2 to plus t by 2. It's a spectral density function, energy density spectral energy density spectrum is like this. So it is f of omega, versus omega. It is like this, and this is nothing but energy density spectrum, that is mod f of omega square versus omega. This is a energy density spectrum, and this is spectral density function. Okay, so for delta omega tends to 0, E naught becomes 2 into 1 by 2 pi mod x of omega square into delta omega. Okay, so it is 2 into 1 by 2 pi into mod x of omega naught square into delta omega is 2 pi f. Okay, 2 by 2 pi gets cancelled, so it will become 2 times of mod of x of omega square into delta f. Therefore, the energy of the output signal is 2 times of mod of x of omega square delta f. Sometimes delta of omega is called spectrum of x of t, where x of omega equal to integral minus infinity to infinity x of t into t power minus j omega t dt. So the above equation describes the way in which a relative signal amplitude or phase is distributed with frequency. If the amplitude is represented with frequency, then it is called amplitude spectrum. That is nothing but the amplitude versus frequency spectrum. And if the in the same way equation represents energy of the signal for different frequencies, hence equation number 1 is called energy density spectrum. Okay, in the same manner, we'll discuss about the power density spectrum. Power density spectrum. So power signals are called periodic signals are called power signals, whereas mm, energy signals are called energy signals non-periodic signals. Energy signals are non-periodic signals. So periodic signals are called power signals. So here power is calculated for periodic signals only if x of t is arbitrary period signal. Power of the signal x of t is given by t equal to limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 mod x of t square dt. That is equation number 1. So this equation number 1 sometimes referred as a mean square value of x of t, and is denoted by x square of t bar, x square of t bar. Okay, so x square of t bar can be represented as it is equal to p equal to limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 mod x of t square dt. Okay, that is the power density spectrum. Next, Parsel's theorem for energy signals. So first of all, we will define the energy. The energy E of signal x of t is expressed as E equal to integral minus infinity to infinity x square t dt. That is equal to integral minus infinity to infinity x of t into x of t dt. But as we already know that the expression for x of t, that is inverse Fourier transform of x of omega, is nothing but 1 by 2 pi into integral minus infinity to infinity x of omega into e power j omega t d omega. That is equation number 2. So substitute equation number 2 in one of x of t in equation number 1, so that it will become t equal to integral minus infinity to infinity x of t into 1 by 2 pi integral minus infinity to infinity x of omega into e power j omega t d omega into dt, interchanging the order of integration, so that it will become 1 by 2 pi integral minus infinity to infinity x of omega into integral minus infinity to infinity x of t into e power j omega t dt whole into d omega. But integral minus infinity infinity x of 24 minus j omega t is nothing but x of omega. But here it is integral minus infinity to infinity x of e power plus j omega t is nothing but x of minus omega. Okay, so substitute x of minus omega instead of this, so that it will become x of omega into x of minus omega into d omega. So e equal to 1 by 2 pi integral minus infinity infinity x of omega into x of minus omega d omega. We know that for a real signal x of t, the Fourier transform x of omega and x of minus omega are complex conjugates. That is x of minus omega equal to x star of omega. So x of omega into x of minus omega equal to x of omega into x star of omega, or it is nothing but mod x of omega square. So E equal to 1 by 2 pi integral minus infinity infinity mod x of omega square into d omega, or it is equal to 1 by 2 pi integral minus infinity infinity x of mod x of omega square into d into 2 pi f. So 2 pi gets cancelled. So it is integral minus infinity into mod x of omega square into df, or it is E equal to integral minus infinity infinity mod x of omega square into df. Okay, so that is the Parsel's theorem for energy signals. Next, coming to the relation between autocorrelation and energy density spectrum. Relation between autocorrelation. Autocorrelation is nothing but J11 of tau. So, arbitrary signal. Let us consider the arbitrary signal x1 of t. So, autocorrelation of this x1 of t is J11 of tau equal to x1 of t convolved with x1 of minus t, x1 of t convolved with x1 of minus t. So that is equation number 1. Here x1 of t is given signal. So x1 of t equal to x1 of minus t, so that it will become convolution. Convolution in time domain, it becomes simple multiplication in frequency domain. So x1 of t convolved with x1 of minus t is equal to x1 of omega into x1 of minus omega, right? Or Fourier transform of J11 of tau equal to x1 of omega into x1 of minus omega. That is equation number 2. So let us prove this. So Fourier transform J11 of tau is equal to integral minus infinity infinity J11 of tau e power minus j omega tau d tau, right? So but integral minus infinity infinity, but Fourier transform of J11 of tau is nothing but according to equation number 1, it is x1 of t converted to x1 of minus t. So this is x1 of t converted with x1 of minus t e power minus j omega tau d tau. But by the definition of convolution, x1 of t converted with x1 of minus t is nothing but integral minus infinity infinity x1 of t into x1 of t minus tau dt, right? So therefore Fourier transform J11 of tau equal to integral minus infinity infinity, replace this by integral minus infinity infinity x1 of t into x1 of t minus tau dt into e power minus j omega tau t omega. So here also two integrals are there. Now we are interchanging the order of integration, so that it will become integral minus infinity infinity x1 of t into integral minus infinity infinity x1 of t minus tau into e power minus j omega tau d tau into dt. Okay, so let us consider this as term A. So here it is delaying version, that is nothing but time shifting property. So x1 of t minus tau is e power j omega t. Fourier transform of x1 of t minus tau is e power j omega t into x1 of omega. So replace this by e power j omega t into x1 of omega. So it is this is integral minus infinity infinity x1 of t into e power j omega t into dt into x1 of omega. Okay, for j omega t into dt into x1 of omega, right? So we extract this x1 of omega outside this interval. integral, that is x1 of omega into integral minus infinity into x1 of t into e power minus of j into minus of omega t dt. It is x1 of omega into x1 of minus omega and square. If tau equal to 0, then autocorrelation function j11 of tau is equal to integral minus infinity infinity x1 of t into x1 of t minus tau into e power minus j omega tau dt. So replace tau by 0 so that it will become integral minus infinity infinity x1 of 20 x1 of t minus 0 into e power 0 dt. So it is x1 of 20 x1 of 20 dt, or it is x1 square t dt. So by substituting tau equal to 0, j11 of 0 is integral minus infinity infinity x1 square t dt, that is equation number 1. Here integral minus infinity infinity x1 square t dt is a energy of the signal x1 of t. Okay, x1 of t. Referring to equation number 1, the value of the autocorrelation function at the origin is equal to the energy of the signal, that is x1 square t dt. So if the signal correlates perfectly with itself, as the signal is shifted with respect to itself, the amount of correlation will be reduced. Hence, the autocorrelation function will be maximum at tau equal to 0. Tau of 0 means no shift. So autocorrelation is maximum at tau equal to 0. Okay, now coming to the properties of correlation. So these are like this. Here we have to note that the J11 is autocorrelation, J12 is cross correlation or simply correlation. Okay, so these are the properties of correlation function. First one is J11 of 0 is equal to integral minus infinity to infinity x1 square x1 square t dt, that is energy of the signal. And second property is J11 of 0 is greater than mod J11 of tau, where tau is not equal to 0. And third property is J11 of tau equal to J11 of minus tau autocorrelation. Okay, this is an even signal, even function. And fourth property is J11 of tau. The Fourier transform of J11 of tau is nothing but mod x1 of omega square, that is 5 times of energy of the signal E of x1. So fifth property J12 of tau. The Fourier transform of J12 of tau is nothing but x1 of omega into x2 of minus omega. Okay, x1 of omega into x2 of minus omega. And sixth property is J11 of tau is equal to J21 of minus tau. It is not J12 of minus tau, it is J21 of minus tau. So first one is J11 of 0 is equal to integral minus infinity infinity x1 square t dt. So states that the value of autocorrelation is maximum at origin. Okay, so j11 of the equal to x1 of t converted with x1 of minus t. So it is nothing but integral minus infinity infinity x1 of t into x1 of t minus 2 dt. If tau equal to 0, it is x1 square t dt, right? So integral minus infinity infinity x1 square t dt, right? And the second one is comparison of a signal with itself is known as autocorrelation. As you already know this, if two signals are identical, then their correlation is equal to 1. As the signal is shifted with respect to itself, the amount of correlation will be reduced. Therefore, J11 of 0 is greater than mod J11 of tau. Here, tau is not equal to 0. And third property is J11 of tau is equal to J11 of minus tau. So J11 of tau is already defined as x1 of t converted with x1 of minus t. It is defined as integral minus infinity to infinity x1 of t into x1 of t minus tau dt, right? So now we can also define this as integral minus infinity infinity x1 of t plus tau into uh, x1 of t dt, right? And then again J11 of minus tau equal to integral minus infinity infinity x1 of t into x1 of t plus tau dt, or it is integral minus infinity infinity x1 of t minus tau into x1 of t dt. That is equation number 2. Equation 1 is identical with equation number 2, right? So J11 J11 of tau equal to J11 of minus tau. And fourth one is J11 of tau equal to 5 times of energy of the signal x1 of t. So J11 of tau equal to x1 of t converted with x1 of minus t, or it is an even function. That's why you can write like this also, x1 of t converted with x1 of t. The Fourier transform of x1 of t is x1 of omega. Taking Fourier transform on both sides of equation number 1, we get the Fourier transform of J11 of tau equal to Fourier transform of x1 of tau converted with x1 of t. So convolution and time domain will become simple multiplication in frequency domain, that is x1 of omega into x1 of omega is nothing but mod x1 of omega square, where x1 of omega square is the energy of the signal x of t. Okay. Next one is phi 1 2 of tau is equal to phi 2 1 of minus tau. Okay, right. Suppose if you take phi 1 2 of tau equal to x1 of t converted to x2 of minus t, if Fourier transform of x1 of t is x1 of omega, and Fourier transform of x2 of minus t is nothing but x2 of minus omega, right? Right. So using the convolutional property of Fourier transform, convolution in time domain equals to multiplication in frequency domain. So J12 of tau is equal to x1 of tau into x2 of x1 of omega into x2 of minus omega, right? So now we see some problems. So find the cross correlation between u of t minus u of t minus tau and e of minus t into u of t, right? So x1 of t is given as u of t minus u of t minus tau, and x2 of t is given as e power minus t into u of t, right? E power minus t into u of t. So cross correlation between x1 of t and x2 of t is denoted by J12 of tau, right? So it is nothing but J12 of tau is equal to x1 of t converted with x2 of t. So Fourier transform of x1 of t is nothing but x1 of omega. Fourier transform of x2 of t is nothing but x2 of omega. So is a convolution property, convolution in time domain, that is x1 of t converted with x2 of t is nothing but simple multiplication in frequency domain, that is x1 of omega into x2 of omega. Here x1 of t is nothing but u of t minus u of t minus tau. So Fourier transform of x1 of t is equal to Fourier transform of u of t minus u of t minus tau. So Fourier transform of u of t minus Fourier transform of u of t minus tau is nothing but if u of t, Fourier transform of u of t is pi into delta of omega plus j omega. Using time shifting property of Fourier transform, u of t minus tau is equal to e power minus j omega tau into u of omega. Similarly, u of t minus tau is equal to e power minus j omega tau into u of omega is nothing but pi times of delta of omega plus 1 by j omega. Now J12 of tau is equal to x1 of omega into x2 of omega. So this is x1 of omega is this one, u of t minus this one. So pi delta of omega plus 1 by j omega minus e power j omega tau into pi delta of omega plus 1 by j omega into x2 of omega is x2 of omega for the e power minus t u of t is minus 1 by 1 by j omega. Okay. By multiplying this, we'll get pi into delta of omega plus 1 by j omega into e power minus j omega tau into pi of delta omega into 1 by pi of delta omega plus 1 by j omega. So taking e power minus j omega tau is common. So it is e power minus j omega tau into pi into delta omega plus 1 by j omega whole square. That is nothing but cross correlation of these two functions. Now we'll see the detection of periodic signals in the presence of noise by correlation. How to detect the periodic signal even though the noise is present. Okay, even though noise is, this is one of the technique. This is correlation technique. This is what we call as correlation technique. So using correlation technique. So correlation technique provides a powerful tool in the solution of the above problem. We shall consider the application of both autocorrelation and cross correlation in the detection of periodic signal in the presence of noise. The noise signal in periodic in practice is a signal with random amplitude variations. As we know that noise signal is nothing but it does not have any constant amplitude or constant time period. Okay, so it is random. It is having random amplitude variations. If S of t is a periodic signal and n of t is the noise signal. Then limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 S of t into n of t minus tau dt is equal to 0 for all values of tau. Okay, so here we are representing S of t in terms of n of t. So it is nothing but 1 by t into integral minus t by 2 to plus t by 2 S of t into n of t minus tau dt, which is equal to 0 for all values of tau. If we denote J Sn of tau as the cross correlation function of S of t and n of t, then J Sn of tau is equal to 0. Why? Because here noise signal is there. So n of t minus tau is a noise signal, S of t is the periodic signal. So that's why it is equal to 0. So J Sn of tau equal to 0. First of all, we'll see the detection by autocorrelation. So let S of t be a periodic signal mixed with a noise signal and not T, right? So then the received signal is f of t, which is combination of S of t and n of t. Okay, that's why f of t can be represented as S of t plus n of t. Let J f of tau, J ss of tau, and J n n of tau denotes the autocorrelation functions of f of t, S of t, and n of t respectively. So then J f of tau is the output received signal is equal to limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 f of t into f of t minus tau dt. But f of t is S of t plus n of t. So it is limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2 S of t plus n of t into S of t minus 2 plus n of t minus 2 into dt, right? So by multiplying this one, we'll get JSS of tau plus JNN of tau plus JSN of tau plus JNS of tau. So since the periodic signal S of t and noise signal N of t are uncorrelated, then JSN of tau and JNS of tau both are equal to 0. These are uncorrelated. Okay, only SS of tau and NN of NN. These are signal, periodic signal and noise signal are correlated. So JSN of tau and JNS of tau, these two are not correlated. That's why these are two are equal to 0. Therefore, JFF of tau is equal to JSS of tau plus JNN of tau. Here JSS of tau is a periodic signal and JNN of tau is a non-periodic signal. Okay, the autocorrelation function of a periodic signal masked by noise is as shown like this. Here, first of all, this dotted signal is first dotted signal. This dotted signal is periodic signal, and it will be masked by this triangular dotted signal JNN of tau. So resultant JFF of tau is obtained as this is the dark line signal is the resultant signal. Okay, so autocorrelation function of the periodic signal masked by the noise. This is about the detection by autocorrelation. Next, we will see the detection by cross correlation. So f of t is nothing but S of t plus n of t, right? So JFC of t, we have to find out JFC of t equal limit t tends to infinity 1 by t into integral minus t by 2 to plus t by 2. F of t is nothing but S of t plus n of t into C of n minus t minus tau dt. Okay, so it is equal to C of t minus tau dt. So the S of t into C of t minus tau dt plus n of t into C of t minus tau dt. So that is JSC of tau plus JNC of tau. C of t is a periodic function and is uncorrelated with random noise signal. Okay, then JNC of tau is equal to 0. Therefore, JFC of tau is equal to JSC of tau. Here, S of t and C of t are signals of the same frequency. It follows that JFC of tau is also a periodic function of the same frequency. It is evident that if the cross correlation of contaminated signal f of t with C of t yields a periodic signal f of t must contain a periodic component of the same frequency as that of C of t. Okay, so the cross correlation of the contaminated signal f of t with C of t yields a periodic signal f of t must contain a periodic component of the same frequency as that of C of t. Okay. So that is one technique to extraction of the signal by correlation, and second one is extraction of the signal from noise by filtering. Here, second technique is filtering technique. Okay, the signal masked by noise can be detected by correlation technique or by filtering. Okay, these two techniques are equivalent only. Correlation, as we discussed earlier, and here we are discussing the filtering, which two are identical, equivalent only. So correlation technique means of extraction of a given signal in the time domain, whereas filtering is exact the same result in the frequency domain. That is only the difference. So these two are the techniques. So okay, in time domain we will use the correlation technique. In frequency domain we will use the filtering technique. Okay, so relation between correlation and filtering. Correlation and filtering. So this relation, what is it? So this correlation technique is used in time domain and filtering technique is used in frequency domain. Okay, we will see this relation in the next class. With this I am concluding the today's class. Okay, in the next class we will see the relation between correlation and